So, let me introduce the concept of stereographic projection. So, what exactly is a stereographic projection? The ideas of stereographic projections existed when you think of how you want to measure distance between 2 points on a surface of a sphere. For example, when you look at maps, typically maps or the globe that you have the longitude and the latitude, and when I want to measure the distance between 2 points on a globe, I actually measure in terms of how much longitude I move within point A and point B, and if there is a displacement laterally, how much latitude I have moved as well. In reality, within a map, which is a flattened version of what I see on a sphere, I cannot measure points between, I cannot measure distance between 2 points by directly exactly taking a linear projection between these two, but I have to see how this has traversed over the surface of a sphere. This is a broad introduction of where stereographic projections are used in real life applications. They are used in navigation systems, whether you are looking at navigations for aircraft or for ships as well. But similar concepts can be used to understand relationship between 2 points which can be connected through an imaginary sphere surrounding a real lattice. So, let us understand what stereographic projection in terms of crystallography is. So, let us say I have a simple unit cell which can be placed in real space, and let us say I have a unit cell which looks like this. So, I have a cube which is sitting at some random orientation like this. And imagine there is a large sphere surrounding this cube, and in this unit cell, let us say I have a plane normal which can be projected in such a way that the plane normal, if it goes and intersects my sphere in the northern hemisphere. So, if I have a sphere and if I have a unit cell, I can think of poles from these unit cell or plane normals from these unit cell, and I can link one projection in this direction, one projection in this direction. So, when I have an imaginary sphere surrounding a unit cell, so suppose I have some kind of a simple cubic system or a simple orthorhombic kind of a system. I have the plane normals intersecting either in the northern hemisphere or in the southern hemisphere, and along the central axis of this unit cell, if I have my north pole and the south pole, the concept of stereographic projection is such that all the plane normals which are intersecting this imaginary sphere in the northern hemisphere, if I connect with the south pole, projections or the plane normals which are intersecting the southern hemisphere, if I connect with the north pole, and if I form a pattern from this points of intersection with the equatorial plane, this projection on the equatorial plane, whatever I see is actually called as a stereographic projection. So, what I am doing now is, in the step 1, if I say I have a real space plane as HKL, I take its plane normal along the direction HKL as well, and this I am connecting to either the north pole or the south pole, and this point of intersection with the equatorial plane, if I now call this as H star, K star and L star, I am transposing a plane vector in terms of a direction vector, and I am taking a projection of a plane as a point on the equatorial plane, and this projection is actually called as a stereographic projection. So, the concept of stereographic projection is such that if I have a pole from a crystallographic plane with say indices H1, K1, L1, by doing this kind of an operation, I can relate it with a single point as H1 star, K1 star and L1 star. And now, if I think of transmission electron microscope as a case where when I am recording a diffraction pattern, if I link the position where I am recording the diffraction pattern as somewhat at this plane from a unit cell which is at the position of the specimen, I can actually link the projected spots that I get from a diffraction pattern to the planes that are satisfying the Bragg's law and giving the diffraction pattern through this kind of a relation. So, to understand this, let us say I have a specimen which is having some kind of a unit cell like this within the electron microscope, and if this is positioned within my specimen area between the pole piece gap inside a TEM, at this point if I imagine a large circle, so let us say now this circle is now intersecting my reciprocal lattice at some points like this. Now, physically these points here are points from my real lattice, but with the definition of reciprocal lattice, remember I introduced that lattice is actually a mathematical concept where I can have infinitely repeating points in 3 dimensions. So, for every single real lattice point, I can have a corresponding reciprocal lattice point where I can relate these two through plane normals. And in addition, I have also introduced this idea that I can now link these with some kind of a stereographic projection. So, now within a TEM, if I can imagine that I have this large circle, in terms of crystallography we call this as Ewald's sphere, and if I link each of these green spots in real space with, let us say, these imaginary blue spots in reciprocal space, I can always link this particular distance that I have. Let us say now this is where I am recording a diffraction pattern and I get a spot pattern. This particular distance I can measure in terms of the camera length, and now in a TEM, let us say if I have the construction like a lens and then I have a specimen here and I am now recording a diffraction pattern at a length L, and let us say from the central beam to get a diffraction spot over here, I have to scatter through an angle theta B1, and let me call this as the Bragg's angle 1. I can link this with the Bragg's law as n lambda is 2d sine theta b1, and this d corresponds to this spacing between planes here. Let me say this is d1, and this corresponds to, let me call this as a reflection g1. What I can do is mathematically, this distance g1, which is the value of this particular point of intersection of the Ewald sphere, and this is where I am recording on a camera in a TEM. Let us say it is at a distance L. This g1 can be linked through this theta b1 through a simple trigonometric relation where g1 over L is sine theta b1. But we know that for very small angles, I am sorry, this becomes actually tan theta b1, but when my theta b, the Bragg angle, is extremely small, less than 1 degree, this simplifies to an expression such that n lambda is 2d theta b, and from here I have theta b is g1 over L. So, if I simplify this, I end up with an expression such that n lambda is d1 theta b1, and I also have theta b1 is g1 over L, and if I use this here, I end up with lambda is d1 g1 over L. And remember, if d1 has indices of h, k, L in the real space, this g1 has indices as h star, k star, L star in reciprocal space. And in an electron microscope, I can link these distances through a simple geometric relation, and let us say if these two are the first order reflections from these planes which are satisfying Bragg's law, and this is again parallel to the electron beam, the projections whatever I record in an electron microscope can simply be linked through this kind of a relation, and this value lambda L becomes a constant, and we call this as a camera constant for electron diffraction patterns. So, now let us say within a microscope I have a unit cell like this, and I start tilting this specimen by turning it like this. So, let us say if I have a set of planes which are like this, these two planes correspond to reciprocal lattice points which are given by these, and if I now tilt it such that these planes are now satisfying my Bragg's law and the reciprocal lattice points go closer, and if I tilt once again, the real space lattice points which are satisfying my Bragg's law, let us say, are like this, and they correspond to a reciprocal distance slightly farther away, I can record diffraction patterns such that, let us say I have a crystal which has a shape like this, and if my electron beam direction is like this, in one scenario I can record a diffraction pattern which looks like this, and here this distance g1 corresponds to, let us say, this length d1 here, and this distance g2 corresponds to this length d2. So, remember, this is a reciprocal lattice projection. So, the distances which are farther away in reciprocal lattice are physically closer in the real lattice. So, that is why I have chosen this d1 corresponding to this g1 and this g2 corresponding to this d2. Essentially, by tilting this crystal, along different orientations like this, I can get different corresponding projections of the reciprocal lattice and I get the diffraction patterns. And in projection of this reciprocal lattice, if I think of any diffraction patterns I get from samples like this, so let us say I maintain one particular tilt axis as constant. So, for example, in these three systems, I had this long axis or this D1 or this G1 as constant. I am changing this G2 value here. So, I actually see the gap between these planes becoming narrower as I orient my sample along different crystallographic planes. Physically, in a transmission electron microscope, by tilting the specimen, I actually start obtaining diffraction patterns which are satisfying Bragg's law with varying G1 or which correspond to physically some D1 value. So, let us say in this case, in this tilt, I have indices as H1, K1, L1. I could have some other indices as H2, K2, L2, and in the third case, this could be H3, K3 and L3. So, essentially if I look at the diffraction patterns now as two-dimensional distribution of intensity and spot patterns which are coming from planes of crystal satisfying for three different lattice spacings, by maintaining one particular direction constant, or in these three cases if I fix this particular distance as G1 and in real space if I call it as D1 corresponding to H1, K1, L1, here I have this G2 changing and then this G3 again some other H3, K3, L3. I can think of this as solving the unknown three-dimensional lattice parameters with three different projections. But when I have one particular axis common for three different projected reciprocal lattice images which are diffraction patterns, I can actually solve the first level of my crystal structure problem, which is knowing the unit cell parameters. And to now start indexing these, we know that in these three cases I had this relationship where lambda L is D1 times G1 and lambda L is again D2 times G2 and D3 times G3. From three different diffraction patterns, I can physically measure what this distance in some reciprocal lattice values is, and through that physical geometric relation which we saw, lambda L is D times G, I can actually get to measure how my reciprocal lattice distances correspond to a real lattice vector, and through this you can start indexing diffraction patterns. So, please understand that when I do electron diffraction, I not only look at the projected information of the reciprocal lattice, but these are also projection of information from the backfocal plane from the objective lens, and then I can physically, through the combination of projection lenses, I can change the magnification and increase the distances and accurately measure what my lattice parameters are and make more sense out of the crystal structure. So, this is the essential concept of reciprocal lattice, symmetry and crystallography, and relating them to electron diffraction patterns. With this, I would like to show you simulation with help of a software on how tilting of a holder changes your diffraction patterns, and then I will show you some demonstration session on how to obtain electron diffraction patterns at the TEM. So let me switch to this software called as Recipro. It is available for free. I'd like to acknowledge and thank Dr. Sato, who has actually developed this code, and it is an extremely useful tool. There is something called as JEMS as well. You can also use this. Let me show you a quick demonstration on the software first, and then we will see lab demonstration of how diffraction patterns are obtained in a TEM, and then we will start learning how to analyze these diffraction patterns. Here is the link to the GitHub page of this particular software, and I'd like to acknowledge Dr. Sato and his team who's come up with this fantastic open source tool. What is particularly interesting is, once you start this software, you can go to this kind of a crystal list and you can choose any crystal structure. So for the simplicity, let me take a single element first to show you what happens when I am tilting a crystal. So let me choose simple gold crystal here, and let me click on this diffraction simulator. We then get this window here, and I can choose to actually orient the crystal in specific crystallographic zone axis. So let me call this as project along axis, and if I say it is 0, 0, 1, I see the diffraction pattern like this now. So for now, before we start learning how to index, let me remove the indices now. So like I was mentioning, from a single crystal gold which appears like this, so if I click on structure viewer, you end up getting this kind of a structure. So if I click on these arrows, I can actually change these axes. So for example, if I rotate in step of 1 degree, and if I look at the structure viewer, let us say I want to see this crystal along a different orientation, I can simply turn my crystal like this, and if I tilt in step of 10 degree, I can end up with an orientation like this. So for example, what I tried to show you here is from a cube which was at zero, 0, 1 orientation. If I tilt this through 45 degrees, I go along 1, 1, 0 orientation, and if I tilt by another 45 degrees, I come to 0, 1, 0 orientation. Physically, in a crystal, this is how my real space tilts look like. Now if I do the same operation on the diffraction pattern, so the projected diffraction pattern of this cube appears like this. So let me go back to the original configuration of 0, 0, 1 orientation. You can see that my crystal here is oriented along 0, 0, 1 axis, and the corresponding diffraction pattern looks like this. Now if I click on this stem holder simulation, I get this wolf net or a stereographic projection kind of a network here, and let us say I want to tilt my holder through a specific tilt angle. So let us say primary tilt is the X tilt, and if I tilt through 1 degree in x-axis direction, I can show you how the diffraction pattern changes. So, by doing a 1 degree tilt, the symmetric pattern which I had like this, so let me do even a smaller tilt, because here is where you know that the Bragg angles are so small that even a 0.1 degree misorientation kind of offsets my diffraction pattern like this. So, I can set my tilt values here. I want to do tilt in steps of 0.1 degree, and here now let me go to the TEM holder simulation and let me do a tilt of. So, I can end up seeing how my X tilt in the microscope misorients my crystal and how the Y tilt in the microscope misorients my crystal. So, this gives you an idea. So, this is an example of how a diffraction pattern from a parallelly illuminated area looks like. There is something called as simulating the Kikuchi band in this as well. I can go here and I can say diffraction simulator, and instead of looking at spot pattern, if I converge the electron beam to a sort of a cone, I get these Kikuchi lines as well, and I can see that when I mistilt my specimen, I actually am kind of traversing on these lines which I see when I converge the electron beam. So, the whole objective of showing this particular simulation and this software is, when I get projected information from a spot pattern, that is through a parallel beam illumination, if I converge the beam, I see these kind of Kikuchi patterns. So, let me see if I can change the camera length here. If I go down to 300 mm, this is typically the length at which I show you the simulation or the demonstration on the microscope. So, if I am now tilting my crystal through a small angle, I am sort of traversing along the Kikuchi bands as a sort of a highway to help you orient a crystal in crystallographic direction. So, for example, when I initially have a crystal which is somewhat randomly oriented and I see some spot patterns like this, and if I converge the beam, if I see a node of Kikuchi patterns like this, I see a node of Kikuchi bands like this, by tilting the holder in particular directions, I can actually bring that node to intersect with the central bright spot, and this is what I am doing when I am doing orientation of a crystal along zone axis in the microscope. So, with this simulation, I have tried to show you an example, and this is what we do when we do orientation in electron diffraction. I would stop here and I will like to take you to the demonstration sessions on the microscope. After we complete the demonstration sessions, from these kind of spot patterns and Kikuchi or convergent beam patterns, let us try to understand what each of these points means and how do we index these spots. So, with that, I would like to end this session. Thank you.